Notice in the event of power loss in the pilot circuit, either holding circuit will drop out. Upon restoration of power, the motor will not automatically restart. Only when an operator makes the conscious decision to restart the motor by actively pressing the forward or reverse button does it do so. A magnetic reversing motor starter, if you think about it, is just like two regular 3-wire control circuits in the same ladder logic diagram. One for forward mode, servicing the forward contactor, wired such that the applied phase sequence is L1, L2, L3. The other for reverse mode, servicing the reverse contactor, wired such that the applied phase sequence is L2, L1, L3. The e-stop, stop, and normally closed overload contact services both the forward and reverse mode. Returning to our previous admonition about simultaneous closure of the forward and reverse contactor, what's to prevent an operator from pressing and releasing forward, and while the motor is spinning clockwise, pressing the reverse button? The answer is, as currently implemented, nothing. While in the forward mode, the F contactor is closed and applied phase sequence is L1, L2, and L3. An operator pressing reverse would also energize the R coil and close the R contactor. Phase 1 and 2 run headlong into each other, and one or both of the contactors explode. It is for this reason magnetic reversing starters must include an interlock, where the term interlock means a method of preventing the simultaneous closure of both the forward and reverse contactor. Interlocks are generally made possible via 3 methods: mechanical, electrical, and push-button. Sometimes more than one method is used. Let's start with the simplest means of interlocking a magnetic reversing motor starter via mechanical means. A mechanical interlock is an interlocking method that prevents the physical travel of one contactor's contact carrier in the event the other contact carrier is engaged. A mechanical interlock is often indicated schematically with a slanted dashed line between the interlocked contactor coils. A mechanical interlock necessitates the forward and reverse contactor be physically paired together. This is often accomplished by a plastic wedge or a plunger fitted between the two contactors, or sometimes the mechanical interlock is an entirely separate device that must slip between the two contactors. When the forward contactor coil is energized, the forward contact carrier is pulled into the coil and pushes the plastic mechanical interlock into the path of the reversing contactor. If the reversing contactor coil is also energized, with the forward contact carrier and armature already pulled into its coil, the engaged mechanical interlock prevents the physical movement of the reversing contact carrier. The same situation occurs if the reversing contactor coil is engaged first. The movement of the contact carrier disallows the physical movement of the forward contact carrier. Whichever coil is energized first is the one and only state that is continually asserted and disallows the latter. If an operator were to press both forward and reverse buttons simultaneously, whichever contact carrier got the jump on the other would be the one and only asserted state, and predicting which one gets the jump is a bit of a gamble. Long story short, don't hire operators dumb enough to think simultaneously spinning a motor clockwise and counterclockwise is a good idea. Notice a mechanical interlock does not prevent the opposite coil from being energized. It simply prevents physical movement of the opposite contact carrier. The opposite coil therefore might experience a premature burnout if this condition were to continue, since inrush current when the armature is not pulled into the coil is substantially higher than ordinary seal-in current when the armature is inside the coil. Let this observation be filed into your troubleshooting bag of tricks when presented with this scenario. If an obstinate operator pressed and released reverse, then pressed and held forward, the forward coil would be expected to experience an early death. It is for this reason we'll step up our game to incorporate an additional level of protection, including electrical interlocks. Contactors ordinarily feature an associated auxiliary pilot contact used for holding purposes. If a system necessitates its inclusion, one can also attach an auxiliary contact block to expand the utility of the contactor. When the coil of the contactor is energized, the contacts in the auxiliary contact block also change states. Consider the inclusion of one of the normally closed auxiliary contacts associated with the forward contactor, F2, in the path of the reversing contactor. Likewise, consider the inclusion of one of the normally closed auxiliary contacts associated with the reversing contactor, R2, in the path of the forward contactor. When the forward contactor is energized, its associated contacts change states, meaning the normally closed contact in rung 3 opens. While in the forward state, the closure of the reverse push button does nothing, since the now open F2 contact prevents the R coil from being energized. Similarly, when the reversing contactor is energized, its associated contacts change states, meaning the normally closed R2 contact in rung 1 opens. While in the reverse state, the closure of the forward button does nothing, since the now open R2 contact prevents the forward coil from being energized. The inclusion of electrical interlocks provided by an auxiliary contact block therefore prevent the coils of the forward and reversing contactor from being simultaneously energized. Note, however, nothing prevents the physical movement of the opposite contact carrier. Consider a scenario in which the auxiliary contact block is broken, incorrectly wired, or is improperly linked with the associated contactor. The contactors may be electrically interlocked, but are not mechanically interlocked. While in the forward mode, nothing prevents an operator from manually pushing the reversing contact carrier in. Additionally, consider a scenario in which one of the contact carriers is jammed or stuck in the closed position. The simultaneous closure of both contactors would constitute a phase-to-phase event. It is for this reason a mechanical interlock can also be introduced to this same system. Here's the pilot schematic for a magnetic reversing starter that is both mechanically and electrically interlocked. The mechanical interlock prevents physical movement of the opposite contact carrier, but does not prevent the opposite coil from being energized. In contrast, the electrical interlock prevents the opposite coil from being energized, but does not prevent physical movement of the opposite contact carrier. The complementary double layer of protection ensures that the forward and reverse contactor are never simultaneously closed. In forward mode, the reverse button serves no purpose and the motor continues to spin in the clockwise direction. In reverse mode, the forward button serves no purpose and the motor continues to spin in the counterclockwise direction. The stop button serves to stop the motor in both modes. If the application warranted its inclusion, a spring-applied, electrically released brake could be added to the motor such that when de-energized, the motor is brought to a rapid stop rather than free spinning to a halt. Finally, consider a third common means of interlocking a magnetic reversing motor starter called pushbutton interlocking. Pushbutton interlocking makes use of mechanically interlocked forward and reverse buttons that when one mode is selected, the opposite mode is deselected. If you want to think of it this way, a mechanical interlock disallows physical movement of the opposite contact carrier. An electrical interlock disallows the opposite coil from being energized, and a pushbutton interlock disallows simultaneous assertion of both states. Note that pushbutton interlocking should only be used in conjunction with mechanical and electrical interlocking and is intended to supplement these methods, not replace them. Note that the normally closed of the mechanically interlocked forward push button acts just like a stop button for the reverse circuit. Similarly, notice that the normally closed side of the mechanically interlocked reverse push button acts just like a stop push button for the forward circuit. The observant among you will note something very, very different about the behavior of this system in contrast to our previous discussion of reversing magnetic motor starters using mechanical and electrical interlocks. This behavior is so different, discussion of this particular magnetic reversing motor starter using push-button interlocking will have to wait until another lecture, since it exhibits a phenomenon called plugging, in that the motor reverses direction immediately without the stop button being pressed. For those that doubt this assertion, I leave it to you to dissect the following scenario. Consider an operator pressing and releasing forward, then pressing and releasing reverse. Aha! Anticipation, as they say, is part of showmanship. Alright, this about wraps up our introduction to magnetic reversing motor starters and interlocks. In conclusion, this lecture took a brief look at magnetic reversing motor starters. We examined the primary schematic using paired contactors and the pilot ladder logic diagram. Additionally, we discussed and compared mechanical and electrical interlocks, and briefly introduced push-button interlocking. Interlock methods are used to prevent simultaneous closure of the forward and reversing contactor. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.